Um, okay, yeah, so let's start. So just see where the edge is. Oh, that's a lovely piece of chalk. Use this. So this was like lecture 0. So big picture. So the aim of these lectures will be to connect string theory with particle physics, and string theory with particle physics. And I guess we can say cosmology as well. But it depends how far we get. Probably it won't be so clear, but we'll get to a point where we can define a string theory model and like start extracting important characteristics of it that are relevant to particle physics and cosmology. And so the general picture will be like, so we start with a string theory model. Something like, let's have a string model. And we will use, we're going to see, you know, like all the different areas of string theory, but there are many different ways to form models in string theory. But I will use the heterotic string. So the heterotic, which we'll define a bit later, and it could be a bit more specific than that, but that's the starting point, just a string model, and we'll always use heterotic in these lectures. And then we want to extract some of the key information that will sort of at least be a step towards getting this important information of particle physics and cosmology. So this kind of important information, well, you know, if you're familiar even in quantum mechanics, you know, you want to know about particles, particularly you define a Hilbert space, right? So you get a spectrum. So a spectrum of particles, spectrum of states that are in the Hilbert space of the model. So spectrum of states. And in particular, usually the massless states will be of interest. Well, I'll just say spectrum of states, but yeah. Spectrum of states, and this is related to a Hilbert space, H. And also another object which like we were just talking about that relates, is another way of expressing information about the states in the model is partition function. Which is usually in like undergraduate physics, comes up in more in thermodynamics. And, you know, if you have a many, but it's also in generally like any systems of many particles. Okay, and there's an analog of that in string theory, which is also contains this information about the sort of content of the model. So to go from the model to this, there'll be a set of rules. So there'll be some rules. And we'll see the most important rule is called modular invariance. The modular invariance, I always say, is the most important thing about string theory. That's my contention anyway. Some people will tell you it's other things, but they're wrong. Okay, and then the idea is that, so you know, if we want to connect it with particle physics, the model of particle physics is standard model. So we essentially want the spectrum of states to sort of be consistent with the standard model. So we sort of want, let's say, the states to like include the standard model, so Sn particles. Okay, and this sort of relates to like, so we'll find that this is related to like the GUT, the grand unified theory. So it's like standard model has a particular gauge group, and we're going to embed that gauge group into our model. We'll kind of talk a bit more about that in a second. And this is obviously relating to particle physics, but we can also look at these properties and say something about, for example, the cosmological constant, which is more related to like cosmology and tells you about the acceleration of the universe, etc. So you could also get other properties. So other properties, in particular, like this, the partition function can be used to give you the cosmological constant. Other properties, yeah, cosmological constant, CC, for example. So that's just a kind of flavor of connecting up with particles and cosmology. And I can write anything else under there. I'll write maybe. Yeah. But yeah, so here we've said, you know, the states will contain the standard model particles. But in general, the space will be much bigger. Like there's loads of states you get from string theory. You know, string theory contains gravity and it contains extra. Generally, it will be a much bigger gauge group and it will contain more states, etc. So there's sort of going to be new ingredients in the model, new components in the model. So the idea is, so then we can say like from here, we have to like interpret like the implications of the model we've chosen here. So that might be like, well, even if we get all the standard model particles or the representations that correspond to them, there's still more to the standard model than just the content of the particles. You've also got things like, you know, you could look at things like gauge couplings, gauge coupling unification, or hierarchies, mass hierarchies. There's sort of like a lot of features of the standard model that you can seek to replicate from the string model. So I'll just put like replicate Sn features. Okay, but then there might also be like new features as well, because we have extra states, extra gauge factors, and so on. New features. We have to interpret those new features. So in the framework we're using, just to give you some example, you know, I think in string theory it was essentially well, under some constraints. Typically, you always get what are called fractionally charged states. Okay, so this is a kind of a fairly generic prediction of string theory, not quite fully generic. Maybe we'll talk about another time, but then there's typically in the model builder we do, there's usually an extra U1 factor, which is related to what we call Z prime. So an extra gauge boson, so an extra U1 that gives an extra gauge boson, which is associated with what we call Z prime. And you could say you could also look at something like axions. So you could look at all the particles in your model, and you can actually quite easily derive things like the decay constant for axion-like particles. Axions are a kind of important topic in beyond the standard model and physics in general, not just from string theory. And then you could look at things like there's a lot of open questions like neutrinos, something like neutrinos. You could look at types of neutrinos you get in the model, etc. And then related to this, I guess you could add related to this, you could think about solving problems. So solve problems. Question mark. So standard model particularly, but also you could say you might try and solve problems relating to kind of cosmology. So for example, like the cosmological constant problem from standard model from quantum field theory, you're not getting the right value for a small positive cosmological constant, for example. So solve problems, question mark. Also something like dark matter. And there's the hierarchy problem. So related to that would be like SUSY breaking, for example, hierarchy problem. So the Higgs mass and the lack of control you get of relating to loop corrections from the Higgs. And then you could get, like I said before, the CC problem. The CC problem, I'll say something very quickly about, maybe something else in a second. So CC problem in string theory is sort of related to the idea of existence of de Sitter. So whether you can formulate string theory with a de Sitter space as the non-compact part of the space-time, and that's proving to be very challenging, and a lot of contemporary research is struggling with. Okay, so that's the sort of thing. So you start with a string model, you get key properties following certain rules. Consistency rules from string theory, anomaly cancellation, or module invariance, and so on. Then you can look at what states you get out, try and see if they're consistent with physics. And then you want to interpret the theory further, which might be like you have to check other features of like known physics from particle theory, but also the new features of the model, and also then think about whether you can shed light on problems, like fundamental problems in physics, like dark matter, SUSY breaking, axions, hierarchy problem, existence of de Sitter, blah, 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 right? That's the kind of big picture. And I guess I could say generally, like a lot of string theorists were doing this kind of approach was very much what they were doing in the early days of string theory. from the late sort of mid to late 80s and early 90s. This was kind of the framework. So you could think of this as like, so what I've just described, let's call that the model building approach to string theory. Okay. So you start from strings and then come down. Yeah, then I guess people got very interested in kind of other things in string theory in like the mid 90s, and then have kind of evolved into other things in the noughties and 2010s. So in the mid 90s there was this second string revolution. People got interested in kind of formal aspects of string theory, so things like dualities, and kind of more on the properties of different compactifications, which we'll talk about a bit more these kind of what these terms mean in string theory in a second. But then recently so a lot of people will look at what are called effective field theories that sort of come from string theory, and then the actual so you have a string theory at higher energy, and then you can also try and see what happens when you run to low energy, and you kind of integrate out heavy states, massive states, and then you get some kind of action, and you can do kind of what people do in other just more standard field theory, effective field theory, and look at the properties and implications of that kind of model. And then related to that perspective is maybe what a lot of contemporary research, a lot of researchers now in string theory are looking at something like the swampland. And I think now probably the swampland approach is maybe more of a almost a catch-all term for this approach that typically starts more by looking at EFTs from string theory, or just the EFTs from quantum gravity. Quantum gravity. And you could also relate this to the supergravity. So the EFTs associated to string theories are typically supersymmetric, and because they contain gravity, they were given this name supergravity, which already as a concept kind of existed in like the 70s and 80s. So the swampland and supergravity approach is more like an EFT approach to string theory, but we're going to be more in this model building approach, just to give you some idea of like where we fit into the space of research. Okay, how long did that take? Let's do. So now I'm going to do like a quick kind of overview of the key things about string theory that we'll be using. I'm a little bit worried about is if I didn't turn the microphone on. No, I think it's good. Okay. Use this. Maybe I can try and use one of these chalks, but I have to. Move it out a bit. Okay, right. So string theory basics or something. Oh God. String. Okay. Let's try this. the string theory basics. So yeah, so the first thing to say is I guess string theory is a complicated subject. In theory, if you wanted to understand all of string theory, it's built on lots of foundations. There's like you need to know like a lot of formal mathematics, a lot of things like conformal field theory, supersymmetry, etc. But that doesn't mean you need to know all of that to do interesting research in it. But yeah, so I guess what we can say is string theory unifies the four interactions. So it contains, in particular, it contains gravity, but it also allows for the unification of gravity with the gauge interactions. And yeah, in particular, there is always a gravity, like a graviton particle in string theory. There's no way to, it's a guaranteed element of string theory. So it's not just that you can get gravities, it's always there. So just a reminder of the standard model. So the gauge part of this is like that you have the standard model gauge interactions. So the color quantum number defining the associated the strong interaction, SE2 left. So it's the SE2 relates to the weak interaction that only acts on the left-handed, so it has handedness, kind of key aspect of the weak interaction. And the U1, which is associated also to the weak interaction and electromagnetism. But then we also kind of keep up with the theory is that there's this spontaneous symmetry breaking with the Higgs that leaves the SU3, the strong force, unchanged, but then it breaks the SU2 left cross U1 hypercharge. So the hypercharge is just a way of the sort of correct quantum number, the name for the correct quantum number of this U1 before electroweak symmetry breaking. And then you're left with just the electromagnetic. So the weak interactions at the energy scale below the Higgs mass, they're gone because that symmetry is broken. Right? So if you're above the scale of the Higgs mass, then you do feel the weak force, but otherwise you go. And then the particles. So I'm going very fast, but we use spin as the kind of key quantum number that identifies the particles. In particular, remember the origin of spin is representations of the Poincare group. So we think that space-time has Poincare symmetry, translations and rotations and boosts. So from relativity, and the quantum numbers for the quantum numbers what we call mass and spin for the representations of the Poincare group. So the spin is sort of like the natural way to quantify particles. So Higgs is the most recent and very important component, and it's the spin zero particle. The scalar, you have many spin half, and because it's a half, not an integer, it's a fermion. And I'm going to write the quarks and the leptons in doublets, which is in twos, which is like the fact that they transform together under SE2, the SE2 of the weak interaction. Okay, and then that's the quarks, and then you've also got the leptons. So the muons and the tau. And these are all left-handed. So the chirality is left. And then we have spin 1, the bosons associated to the gauge groups, gauge interactions. So we have the gluons. Maybe I'll just write these. So gluons. I don't know what I usually use. So G or something, and then W plus minus and Z. So the W plus minus has charge, and Z doesn't. And then you also have antimatter. The antimatter of these so that's the content of the standard model. And then just a reminder of problems of the standard model, which we'll be kind of wanting to sort of solve, I guess. So there is, say, 19 free parameters, more or less. So you've got the masses of the electron, the muon, the tau, the masses of the quarks. You've got 3 theta angles, a delta, the gauge couplings of 3 forces, and the QCD theta, and then the mass of the Higgs, so the Higgs Bev. I think that's 19 maybe. Then there's also dark matter. So we don't know how to account for the observations from astrophysics around dark matter, or the cosmological constant value. Also, you could add things like gauge coupling, unification, strong CP problems related to axions, etc. So there's many things you could add here. Hierarchy problem is, I guess, also related to having 3 parameters in some sense, but the hierarchy problem kind of makes the theory is a real fundamental problem, which I should just emphasize. And I could also say here that supersymmetry was sort of like, the original idea was that it could solve some of these problems, and in particular the hierarchy problem it does solve, because if you have a symmetry between bosons and fermions, these high loop corrections to the mass of the Higgs don't kind of get kind of balanced out by the existence of the supersymmetric partners. But then if you do there's no experimental evidence for these super partners, so supersymmetry hasn't really proved to be verified. Hopefully we'll talk a bit about supersymmetry and string theory at some point. But we will also find that there are non-supersymmetric string models, which could be motivated by this fact that there isn't any experimental motivation for string theory, for supersymmetry or string theory. The other thing about supersymmetry I could mention is that, just to be kind of precise, so the supersymmetry, did give a solution to the hierarchy problem. It naturally gives a 0 cosmological constant, which doesn't explain the small positive value for it, so it's not quite solving the cosmological constant problem. And it also was good in that if you combined it with a gut, like a larger gauge group than this one, so a gauge group that contains this, and then you had supersymmetry as well, then you could do like gauge coupling unification, would work nicely. But you needed SUSY as well for all the gauge couplings to unify at a specific scale. So the 3 gauge couplings, you have a gauge coupling associated to the strong, and then a gauge coupling to the SU2, and a gauge coupling here, or whatever, and then these sort of 3 different scales, but then at different energy scales they have different values. And then if you have supersymmetry in a gut, you can make them meet. was kind of like an important early result in supersymmetry. Everyone in the 70s and early 80s, everyone was excited about SUSY guts. But anyway, that's not string theory. So now we'll do some quick overview of string theory. That was more of a standard model basics. But anyway, that's just a very quick background to kind of problems that we're trying to answer. Okay. So in string theory, so a very basic way to introduce string theory would be to think about how in relativity courses, you talk about how you've got, if you think about it, you've got particle zero dimensional, and it's this now in space and time, and then it moves right on some line. It's zero dimensional, and then it creates a one-dimensional line as it moves through time and space. This is the world line. Okay, and you usually, it's typical to use a parameter tau for the parameter along the world line. And then let's say, it's the position of the particle as it moves along the world line is given by x mu of tau. Okay, so the idea of string theory, you could say, is, well, what if we added a little bit of dimension to the particle? So instead of the particle being the zero-dimensional point, it now has some like length, right? But then if it has a length, then instead of it being a single line, then it's going to move into a sheet, like a two-dimensional space. So it's going to have not just one parameter tau, it's going to have two parameters, which we usually call like tau and sigma. So instead of it being x mu tau, we're going to have x mu tau and say sigma. So let's say like this is tau and this is sigma or something. And then this is now, instead of a world line, a world sheet. Particle, because it's one-dimensional, is called a string. Just a one-dimensional object. That's the sort of starting point. And then what you do is you go, okay, well, people have already done quantum field theory with zero-dimensional particles and so on. So what happens if you do it with a string, like with a one-dimensional object, fundamental object with a length? And it turns out in strings, like, not only as soon as you posit the existence of this extra length, so one-dimensional object, it also means that once you construct the theory, you automatically will have objects which are higher dimensions, like internal dimensions. So not just one-dimensional, but you get objects which are already two-dimensional, and then they move through space and create a three-dimensional thing that's bigger than a world sheet, and that's called a brane. Right? So string theory, automatically it turned out that it took a while for people to work that out. But you always end up with these higher. So you can't just do, it's like if you do zero-dimensional quantum field theory, you get everything stays point particles. You just have point particles, but string theory, like naturally these higher, you try and do one-dimensional objects, and then you'll automatically get the hierarchy of high-dimensional ones, which is interesting. But we won't talk so much about branes because It's not actually in the string models we use. It's not actually relevant, really. But anyway, right. So then the idea is that now we have a string that's given by like x mu tau sigma, okay, and that's going to be, this mu here is a coordinate on the space time, so that would have like if you're in 4-dimensional space, mu is like 0, 1, 2, and 3, and they're the 4 dimensions, time and space. But then it in general might be a d-dimensional space-time, because what we'll see is that actually it can't just be 4-dimensional. But so this mu, the point is the label of the space-time dimension. But these tau and sigma is important to think they're parameters of the string itself, of the world sheet. So these are world sheet coordinates and this is space-time coordinates. And it's important to distinguish those two. And in that sense, we can think of x for this function x as really like a function that takes in tau and sigma, then maps you into the space-time by giving you mu. So I don't know what my picture is supposed to be doing here, but like x. So let's say that the tau and sigma are your coordinates within a space sigma. So the world sheet is capital sigma, and then tau and sigma, lowercase sigma give you the coordinates on the world sheet, capital sigma. So x is a map really from the world sheet, capital sigma, to some space-time n, which we will say is actually, just because we don't want to assume it's 4-dimensional, d, it's d-dimensional. So mu runs from 1 to d or 0 to d minus 1. Okay, and the kind of key part, so if this is space-time, this space here, so we have some n, m, d, then in general, this is some, like d-dimensional manifold, some space, and it will have in particular some like metric. Okay, and we'll come back to that. But oh yeah, I should have said here as well, like we've got basically two types of strings. A string that's like this, circle, goes and creates a tube, and then we've got a string like this, which is just a line that goes and makes an open sheet. So this is called an open string, and this is a closed string. Okay, and so now instead of in quantum field theory, you have points where you have Feynman diagrams that describe how the point particles come, meet each other, interact, and then go off. So that's what a Feynman diagram is. So now what we've got to imagine is you've got like strings that come in, interact in whatever interactions the string model contains, and then they come out. So it could be an open string, a line, or whatever, and then they come in and create new strings, or it could be closed strings coming in, creating new strings. And what sort of has some intuition behind it is that if you have an open string, if you have two open strings, for example, and they're coming in to interact, they can connect and form a closed string. They join together. So if you have open strings, they can turn into closed strings, but a closed string coming in and meeting another closed string, there's no way for them to they're closed, they're not going to join together and create a open string. They're always going to have closed boundary conditions. So basically what that tells you is that string theories that contain closed strings don't have to contain open strings, but strings that contain open strings have to contain closed strings as well. So there are different string theories, and some of them, yeah, are just closed string theories. And we work in heterotic, which only has closed strings. So we will only look at closed strings. Okay. So yeah, so then you can think of like, you can build off your kind of QFT knowledge a lot. But what you want to do is something similar to what you do in QFT. You have a string which is described by this function x mu of two coordinates. You want to build an action that obeys Poincare symmetry to relativistic. It's a relativistic, the invariant theory, and so you're going to get something very similar to like a Klein-Gordon action if this is like a boson, for example. And then if you think like when you do quantum field theory, you also have fermions, right, which have a Dirac action, so spinners. And we have a similar thing in string theory. If you have a field that's now got, you know, fermionic statistics instead of bosonic statistics, this would also be a map from the world sheet to the manifold, but it's a spinner. And so this would also depend on, you know, this would also map tau and sigma to like indexes and index in space-time. But it would, you know, it would form a spinner representation under the Poincare symmetry of the MD. So, so the idea in string theory is you want to build a relativistically invariant action for a one-dimensional fundamental object. And that's just like basically a generalization of a Klein-Gordon action for X and a generalization of a Dirac action for something like psi, mu. Okay, so I'll write that here. So you've got something like Sx, which is going to look like, so more or less, you know, maybe ignoring some prefactors. An integral over the world sheet. So tau and sigma, so it's be like integrating over sigma, capital sigma. And then, well, we're going to have something here which I'll write in a second. But first, you've got something that looks like your Klein-Gordon. So it's like D. So I'll write a little d instead of a covariant d for now. But so d alpha x x mu d beta x x nu. Okay, so then you're going to have some, probably need a, let's say we have, let's say our space is Minkowski space. So we have a metric. So let's say this is just Minkowski metric. So then, I don't know, eta mu nu. And then there's a scale factor here. So there's something here which refers to the kind of like the volume of the world sheet. So there's a similar thing if you do a one-dimensional world line. You kind of, the length of the line appears here in the integral over the world line. But here you have an area, and you know, if you have an area of the surface, it's like a determinant kind of. So there's sort of like a determinant here of, so a determinant of like the metric of the world sheet. So let's say this has a metric h alpha beta. So this is going to be determinant h alpha beta like that. Okay. So it's kind of, it's just a generalization of a Klein-Gordon action basically, but with 2 dimensions. And then you have something like for the psi, so this is going to look like the Dirac action, ignoring some prefactor, integral over the world sheet. And then you're going to have a similar thing like, so let's call H is just the determinant of H alpha beta. So you got this area prefactor in the integral. Then you've got a Dirac-like thing here. So psi mu bar, and then gamma matrix with some spinor index and a couple, multiplied by derivative. So I'm using little d because we're in Minkowski space. And then alpha, and then capital psi. Maybe I could put the mu on the bottom. Something like that. Okay, and so this looks like the Dirac kinetic term of Dirac, right? So this would be like if you had a massless, this would be like a massless spinor, massless spinor field. And so what we've tried to do here, like I said, we're supposed to have Poincare invariance. So we've got Poincare. So if I write the symmetries, okay, then we've got Poincare. But then there are additional symmetries. So Poincare is obviously a symmetry in this space-time, the MD, but then there's also symmetries associated actually to the world sheet. So I'll just put world sheets, or let's say sigma symmetries. Okay. So these are, the first ones are like reparameterizations of tau and sigma. So we can sort of rescale tau and sigma in coherent ways, relabel, reparameterize, and have the same physics. Because like the way you label these two coordinates shouldn't change the physics. So this is a reparameterizations, also called diffeomorphisms. Diffeomorphisms. So they're kind of like, kind of boring standard thing, just reparameterizations. And then, so that this would be like if it's like having a Jacobian of, so you have something like, say you have two derivatives multiplying the metric. So if you had like, so we call them the world sheet metric H alpha beta. So it'd be like H alpha beta multiplied by, you basically your Jacobian of your coordinates, tau and sigma. And that's just reparameterizing all the reparameterizations of tau and sigma. So the physics should be invariant under that. Then the other one, which is much more interesting and important, is what's called Weyl symmetry. So Weyl symmetry, or Weyl symmetry, is the fact that just by writing down the relativistically invariant action, it turns out that there's an additional invariance here. So in particular, we can rescale the world sheet metric H alpha beta by a exponential, and nothing changes. The equations of motion, the theory doesn't change. And that wasn't something that was predicted. So these are essentially like Polchinski actions. And I don't think Polchinski knew that he was going to get this when he wrote it down. It was just a result. So H alpha beta can be rescaled by like an exponential So some scale factor in the exponential, like let's say what should I call it? I don't know, phi. And the phi depends on, I guess, tau and sigma. Okay. So it's like a local, the phi scale factor, it's like a locally, depends on the tau and sigma. Okay. And this, so theories like, so even before string theory, you could write down, and people did write down, point particle quantum field theories, which had this symmetry essentially, or had a symmetry like this, kind of a rescaling of the metric like this. So those theories were called conformal field theories. So conformal symmetry is precisely this, basically. So this makes string theory equals a conformal field theory, or CFT. All this bit of the board so this doesn't work. So yeah, string theory is a conformal field theory. Okay, and okay, so that's like, really will turn out to be very important for us. So one tiny thing to just say here is, let's say we have a theory with just x and psi, and these we said are massless. There's no mass term for either. So what we'd have is actually we'd have d massless bosons and d massless spinors here, like one for each mu. So if we have these two terms in our action, we'd also have supersymmetry. And I won't write it down, but you could write down specifically the, I can write down maybe be something like, well, you can kind of double check, but supersymmetry would be like, so if S is Sx plus S psi that I wrote here, then it's supersymmetric, SUSY, and in particular the transformations between the x and the psi. So you could do an infinitesimal transformation of x, mu, that would be something like spinor parameter, and then I think like psi bar mu or psi mu, whichever, and then you could also do, transformation to go the other way as well. So delta psi mu be something like epsilon, then a gamma, gamma alpha, delta alpha, x mu. But yeah, so what you would have if you just had this and this is a theory of d massless scalars, d massless spinors, which have supersymmetry according to these transformation rules. You swap x mu with psi like this, psi with x like that, and then they just transform into each other, same theory. So you'd have a symmetry between the number of bosons and the number of fermions, which is kind of what we expect from these two actions. Okay, so maybe that's a good place to stop. And we see if I had anything. But yeah, next, so what we do next time is start talking about the conformal field theory aspects of string theory, and seeing why the fact that we have conformal symmetry is going to be so important for us. Okay. All right. Yeah, indeed. Nice.